So we have talked about how to graph sine and cosine. So can somebody, everybody needs to be able to do this right now. So whatever paper you got out, can everybody please just graph a simple sine function, right? F of x equals sine x. You graph, whoop, there it is. Whoop, there it is. We got it. Whoop, there it is. So try just to graph that. Give me some scale. Graph one cycle of this. It's not been moved, it's not been stretched, it's just a poor little sine dude. Minding its own business. We're going to graph the hell out of it. Oh boy. There it is. So we're going to graph one cycle. We normally graph a cycle beginning at 0 just to make it easy on us. I could graph a cycle starting any damn where. This is always going to have the same kind of shape, right? Just to kind of catch up, you guys, what kind of scale are you making here?
Pi over 2.
Yeah, pi over 2.
Pi.
Pi.
3 pi over 2 and
3 pi over 2.
2 pi.
Just to remind you guys, this is the positive y-axis, right? Negative x-axis, negative y-axis, and then back to the positive x-axis. You guys, so you can kind of keep in mind the unit circle. We're just kind of going around that sucker. Where does sine start?
0.
It's 0. I love it. Sine likes y, and I started the x-axis, so sine doesn't like it there. What's the highest sine is going to get?
1.
1. What's the lowest sine is going to get?
-1.
Negative 1. Cool. So, would you all agree there's 1, 2, 3, 4, 5, and I call them something weird, I call them anchor points. Because they're the anchors, and then I can kind of put the lines over the top of them. And that means that there's 1, 2, 3, 4 steps to get through them all. Does that make sense? Okay, so for sine, I start at 0. Where do I go from there?
1.
Yeah.
1 for pi over
So now I'm on the positive y-axis, so I'm up at 1. Then I go to 0. Then I go to negative 1. And then I go to 0. So, real quick. Everything we just did, whatever the shit the period is, and whatever my steps are, sine is always going to hit those. Unless, of course, it's been like stretched or it's been compressed. But even if I compress it, it's still going to hit these values at each step. That's why I took some time to talk about step size. How big is each step I'm taking for a function that hasn't had nothing done to it? How big is each step I'm taking? Pi over 2, right? Pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. And what's the period of a unshifted sine function? 2 pi. I love it. So 2 pi cut in fourths is pi over 2. I can figure out how big each step is going to be. How long until I go from one anchor point to the next one, to the next one, to the next one. And then I just got to connect these. Okay. Sound effects not required. So if I do a little funky stuff to this, what you got, Jeff? Sure. Okay. So I've done a lot of funky stuff to it. Dear God, Jeff, why? I know it's going to have this shape. I know it's going to hit these major ideas, right? 0 maximum, 0 minimum, 0, right? And those going to hit those. Can somebody tell me what the amplitude is going to be?
3.
Insane. So instead of going up to 1 and down to -1, it's going to go up to 3 and down to -3. Okay, cool. So that's pretty simple. I can handle that. Can you tell me how to get the new period? What part of this is related to the new period?
Coefficient of x.
Yeah, the coefficient of x. I love it, right? And again, why does that make sense? That is the number that is affecting my domain. That's the number that's affecting the inputs. So that's going to affect this motion here, right? So if I'm multiplying, all my inputs can be smaller than they used to be. It's going to compress it. So we give it the letter K. What's the K? You just told me. What's
2 pi.
K? 2 pi. So what's the new period?
1.
2 pi divided by 2 pi. I love it. 2 pi divided by K. 1. So for any trig function, the new period is going to be the old period divided by K, divided by the number in front of x. Okay. And again, we explored why that makes sense, so now I can just sort of like shortcut that and just get the number I need. How are we all doing so far? Okay, thank you for that. There's one thing I didn't talk about last time, and for some reason I decided to make this extra funky. So let's see if we're all cool with this. I'm gonna ask you for this, and it's not gonna affect how I graph it. It's just gonna be sort of an extra little check that I can make. So do you remember, if I have a parabola, can't I do something to make it like move over?
Yeah.
Right? So if I put x minus 3 inside of a parabola, it's gonna move to the right 3. We talked about that, right? X minus 3 squared, it's gonna move right 3. So for any other function, we just call that a left and right transformation. We call that a shift. Here, for a trig function, we call it a specific kind of shift. We call it a phase shift, right? There are reasons for that because trig functions can be used to talk about, for example, electromagnetic waves, so forth. So the idea of phase, things being in phase, the frequencies being in phase, all that kind of stuff. So we're not going to get into all that. I'm not going to make this into a physics class, even though part of me would love it, but no. Just to let you know that where that word comes from. What the shit is phase? Well, it has to do with what we use trig functions for higher stuff. So we just call it the phase shift. That's left and right motion. In order to figure this out, I need to know what is happening to the x, a plus or minus. So this is not the phase shift, because that's not what I'm adding to x. Do you see that? That's what I'm adding to 2 pi x. All right. So don't write this down. Let me do a little side note. I should have started with an easier problem, but I'm just insane. Just watch this. So if I had this is easy. The phase shift would be 1/2. In which direction? Who remembers?
The right.
Yeah, right 1/2. Okay. That's easy because x, I'm subtracting 1/2 away from it. Ooh. So if I had this, the problem is I can't see what's happening to the x. I see what's happening to the 3x. I don't know what the shit's happening to x. So can you factor the inside? What comes out? 3, right? What are you left with?
X minus 2.
And why is there a 2 there? I'm going to make a big deal out of this. It's going to be weird.
6 divided by
Because what was there, divided by what I took out, is what's left. And you're like, yeah, Jeff. Yeah. The reason I made it really, really overtly like, dude, because we're going to get some weird shit, like the one we're doing right now. So what's the phase shift here? By the way, notice phase shift has become PS, because I don't like to write a lot, because I can't.
2 to the right.
2 to the right. Kick-ass, right? Is everybody with me? Now, this one, so let's just focus on this, because I just got to factor the inside expression. This one's going to suck a little bit. And you can always tell exactly what you got to take out. It's basically K, because I need the X by itself. So you never know, you never are not aware of what you need to take out. It's just how the hell do I take it out? That's the hard part. So what am I going to take out? 2 pi. So here, I'll do half of it. There, okay. Now, why is this in x? Because 2 pi x divided by 2 pi is x. Is everybody with me? Pi over 2 divided by 2 pi. You could even do this if you want to. I wouldn't really, but oh well. Don't I have to divide it out, right? Okay. Now here's what I would do. Didn't I take the pi out? I wouldn't do this, to be honest. I would do this. Didn't I take the pi out? Yes? Isn't the pi coming out? Yes. So there's a 1 here. Didn't I divide it by 2 also? I'm dividing it by 2 pi, correct? So the pi's cancel, yes? It was already being divided by 2, and I divided by 2 again. So what am I dividing it by now? 4. There. You can check it. What's 2 pi divided, if I multiply this back in, what's 2 pi divided by 4? 5 over 2, which is what that was, yes? Okay, I like it. Let me stop for a bit. But now can you tell me the phase shift? Left 1/4, is that cool? Okay. For us, because of what I've shown you, I am never going to have to apply that to graph. It's just going to happen, which is awesome. But the book will ask for it, so will I. I want to know what the phase shift is, but you're never going to have to directly do anything with it. It's just going to come out of the work that we do. So everybody's semi with me. So we talked about transformations by themselves. If I want to know how much it moves left and right, I need to know what is happening to the x. So if I got shit with the x, I got to get that the hell out the way. So then I can see exactly the x has a plus 1/4, so I know it's going to move back 1/4. Yes?
So, say it's still 2 pi x plus a fraction right there.
Yeah.
But the fraction wasn't pi over 2, it was like 3 over 5. How would you go about doing that?
That would be gross as hell. I would never ask you to do that by hand. Do you understand? Because then you're going to get exceptionally funky things. So we're going to be doing these by hand. Yeah. Yes, I know your calculator can graph these, right? So it could pass the class. Good for it. We're going to be doing this stuff by hand. So I'm not going to give you one that's you're going to have like 3 over 5 pi, and you're going to have to graph. No, you have to plot that. Are you with me? I'm not going to do that to you. Okay, I'll do something like this to you. Yeah. I can handle that shit. Okay, maybe. Yes?
So you divided out the 2 pi, then you got to 1 over 4.
Totally.
So like you
Just to check, I multiply this back in to make sure that it got back to where it started.
Gotcha.
So whenever you divide something out, you can check it. Take a minute and multiply back in. Just to make sure you did that right. Does that make sense? If you don't do that, you don't make sense to me. Especially when it's weird-ass numbers. Just take a minute, multiply back in, and go, oh yeah, I get back to where I was, so I must have done it right. Does that make sense? You can always do that. Anytime you factor anything, you can always just multiply and make sure you get back to where you started. Okay, how you guys doing? You look appropriately excited.
Sure.
Which means not. Okay, yes?
So I just wanted to check with the phase shift. So when we took out the pi's, we just did 2 over 2, just to give us 1, and then we just did
Alright.
1 over 4, right?
Where'd the 4 come from?
Because there's 4 places in the graph.
No, we're not doing that.
Steps?
Okay, so let's look at this by itself. Okay.
Okay.
Okay, so that's inside the cosine, correct?
Mm-hmm.
Okay, so I'm just going to look at this by itself.
Okay.
I'm going to take a 2 pi out. So here's something else you could do. You ready? All right. If I divide by 2 pi, is everybody cool with this? Divided by 2 pi, isn't that the same thing as multiplying by 1 over 2 pi?
Yes.
Okay. So look at this. Now that you can actually work it out, right? You can do this every damn time you take anything out. If it's fractions, write it like a fraction. Now let's see, how does this work out? The pi's cancel. On the bottom I get 4, and on the top I get
1.
No.
kabam.
And then you put 2 pi over 4.
No, and that part was just to check it. It's not part of the work. If you want to check to make sure you did that correctly, you can multiply that in.
Oh, okay.
But you don't have to. That's just a check. Right now I can see the phase shift again, right? It's still left 1/4.
Okay.
You can do that every damn time. Because you have to do it every damn time. Whenever the coefficient here is not 1, I've got to take that stuff out of the way. And I really want this to make sense. Because I need to know what's happening to x, not what's happening to 2 pi x. I don't have a 2 pi x axis, I have an x axis. I need to know what's happening to x, so I need to get that shit out the way. Does that make sense? If it doesn't make sense, it's just what you do. And I don't like that, but I won't. Okay. Alright. This, I need you to understand. You need to be able to do this, but I'm really not going to use this to graph. It's just going to kind of happen, but it's a nice check. I know I'm supposed to start now at negative 1/4. Do you guys see that? Normally I start at 0. If I shift everything back 1/4, I know I'm supposed to start at negative 1/4. So let's see if that comes out of the work. How do I do this work? I want to see where I begin. Where do I normally begin when the inside is 0?
0.
So I'm going to set it equal to 0. Then you're going to solve this. So there's, you should not be surprised that there is some algebra in this class. Does everybody, I want to see if you guys are cool. Does everybody see how the pi's cancel? Because they're going to divide by pi, is that cool? So then I get 2x plus 1/2. That looks so much better, yes? So then I can, how do I solve for x?
Move the 1/2 to the right.
Subtract 1/2,
Divide by 2.
divide by 2. And I got exactly what I knew I should get. I knew I should go left 1/4, and sure enough I start at negative 1/4. So as some of you guys get more confident doing this, you don't have to do you don't have to do the begin, because if you do the phase shift, you know where you're going to begin. But it's kind of nice to see the same number coming out. You're like, okay, everything's checking, good, good. How do I do to see where I end? I normally end where?
2 pi.
Yeah, 2 pi. I normally end at 2 pi. So can I kill the pi's again? Yes.
Yes.
All the pi's cancel. So I get 2x plus 1/2 equals 2. Alright, where do I go from there? Subtract 1/2. What's 2 minus 1/2?
3/2.
So 3/2. Is that cool? And then I'm gonna
Divide by 2.
divide by 2. And this is a cool trick. I don't want to write a fraction inside of a fraction, so I just did this trick, but division by 2 is multiplication by 1/2. If I have fractions, I'm going to keep things like fractions, and they work together. So where do I end?
3/4.
3/4. Does that match with the period? What's the period supposed to be? 1. What's 1 above negative 1/4? What's 1 plus negative 1/4?
3/4.
3/4. Hey, all right. So there's a lot of like repetitive stuff, but when you're first doing this, it's nice to see you have all these checks and balances. Did you do this right? Yeah, because it matches with what the period's supposed to be, and it matches with what the phase shift's supposed to be. Kick ass. Then I know I'm on the right track. So let's try to graph this thing. Okay, here we go. I'm gonna collect all of the important shit we just figured out together, because I got it like spread out. So let me collect all the stuff we got. We got the amplitude is 3. We got the phase shift is back 1/4. We got the beginning at negative 1/4. We got the ending at 3/4. We got did I put the period yet? No. Period is 1. What's the step size?
1/4.
Good. It's always the period divided by 4 because I take 4 steps to get to all the important points, just like we saw here. 1, 2, 3, 4. So I need you to understand, if I just figure out how big each step is, that tells me when the next most important point's going to happen. And the most important points on the sign is, where is it 0, where is it 1, where is it negative 1. So now we got everything we need. I'm going to start at negative 1/4. What really kicks ass is my step size agrees with my start. They have the same denominator already, right? you guys see that? Alright, some of you guys are like looking at me like, can you start making sense now? Okay. I don't know if you remember, I had to change the denominator if they didn't match, but can you step by one step? Can you go one step? Or if I take one step up, where do I go? Zero. If these didn't have the same denominator, wouldn't I have to be careful? Wouldn't I have to make the same denominator? Same denominator? That word is weird sometimes. So if I take one step, I'm at zero. If I take another step, I'm at 1/4. Another step, I'm at 2/4. Another step, I'm at 3/4. And does that match with where we said we're supposed to end? Yes, I took 4 steps. 1, 2, 3, 4. Did I end where I was supposed to? Can we stop for a minute? Yes.
This may be, so like, when we solved it to get to, when we solved the begin and the end, and then you said that we could just cross out the pies, right? But then what kind of popped into my mind is, why would you do that if you're not supposed to divide by some, like, just take it out if you're adding or subtracting?
No. We if it's in every term, I can divide by it. So, for example, if I had to solve this equation, couldn't I just divide both sides by 2?
Okay.
If I wanted to, right? That's all we're doing. We just saw if pi is in every. So if I had this.
Or like more than one term.
If I had this 4 pi x plus 8 pi x squared equals 7 pi. First thing I would do is divide everything by pi.
Yeah.
Because I'm doing the same thing to both sides, right?
Yeah.
Completely legal. And that, while it still looks gross, looks a lot better. Yeah, okay. So that's all we did was divided each piece by pi.
Could you go back to when you were solving for the end point?
I have a handout, by the way, in a minute, because I know when I do it, it kind of gets all over the place. I got a little handout for you guys. We're gonna do. Now, real quick. I'm sorry. Did you get on?
It's okay. I'm good.
Got it? Okay. How far up am I gonna go? Careful.
3.
3. So 1, 2, 3. And then I'm gonna go down, of course. What's the midline? Y equals 0. I love it. The only way that could change is if my equation had like a plus or minus something over here, so it would move the whole thing up or move the whole thing down. Okay. So sine, right? I'm starting right there. That's where I begin. Where does sine start? What's the output? Yeah, sine starts at 0. Then it goes to the maximum. And then back to 0. And then back to the minimum. Back to 0. See, that's the power of doing this period and the fascia, not the fascia, but doing the period and the step size. Because those are where those important points are happening. So I don't care where I end up, sine's got to hit those things. It's got to. That's how sine works. So now you just got to fill this in. Okay. Can somebody tell me what if that first number had been -3? What would have happened? So at 0, I'm at 3 for this. But of course, if that was a -3,
Flip the shape.
I would have been down here, right?
Yeah.
So the outputs just get multiplied by negative. So really, visibly, this just
It flips.
flips, yeah. So it would go down, and then up, and then down, yeah. Okay, you guys with me? That's all that would change if the first number was a negative. Yes?
So, if you were to put a negative in front of the 3, wouldn't that kind of also be the same as shifting it over to the...
No. Careful. Alright, so real quick. Let's see, let's just do cosine, sure. So if I do this, that is a what kind of shift?
That's a shift to the right.
shift to the right. If I do this, what kind of shift is this?
Vertical.
Shift up by 2, right? So then the midline would go to 2. So cosine would oscillate around 2 now. Does that make sense? Okay. This multiplies the outputs. So if it used to go to 1, now it's going to go to 3. And this would just say, if you used to go to positive, now you're going to go to negative. So effectively, it just does this to the graph. My outputs become the opposite sign of what they used to be. Yes?
Could you go back to when you were saying oscillating, because I missed that part.
Oscillating? Oh. Looking at this, we're not going to graph this because it would be highly weird, but where's the midline now?
Midline is at -3?
No.
No.
It's
With
just
2?
Well, let me take this out. Let's just focus on one thing. Yeah, so the midline would be at 2 now, right?
Yeah.
Is that cool?
Yeah.
So what I mean is, instead of cosine doing this around 0, it's now going to do this around that midline. Wherever the midline goes, that's what I'm going to oscillate around.
Okay.
Do y'all agree with me that the sine function, a normal sine function, oscillates around the x-axis, correct?
Yeah.
The midline is y equals 0. If I put the midline here, now it's going to oscillate around that. That's the importance of the midline. It's just saying, what am I going away and coming back to? What line is that? The only way I can change it is if I have a plus or a minus out there. That would move the whole thing up or down. Okay, now, let me give you this handout that I definitely put somewhere. Here, okay. Oh, did we, wait a minute. Did we do this yet? Did we do this one?
No.
I don't think so. Okay. So this is on the other side of this sheet. So let me ask one more time. Anybody need this sheet? Yes, okay.
This is right.
Yes. So let me show you. It should say graph and trig functions. Yeah. And it's got one completely worked out problem. So if I were you and I'm doing this crazy ass homework, I'm having this shit sit next to me. Yes? That's one reason I give you these worksheets. Is I'm hoping you have them sit next to you as you do the homework. You can't have them sit next to you when you do the test, but my hope is as you do problems, this kind of gets in your head. That's the hope. Okay. Oh my goodness, my life is all paper. Okay,
Paper.
you guys, I'm tired. You guys do as much as you can. I'll catch up to you. Feel free to work together if you want to. Oh. You need one? Okay.
Yeah.
Alright, let me catch up to you guys. What's K?
2.
What happened?
Oh, my thing.
Yeah, 1/2. Okay. What's the amplitude?
2.
2. There we go. So what's the new period going to be?
1 pi.
2 pi divided by
1/2.
1/2. 2 pi times 2. Kick ass. Phase shift.
5/4.
5/4
To the right.
to the right. Kick ass. So now I know I should be beginning at 5/4 because I normally begin at 0, right? And when I do the begin thing, I'll kind of like see if that comes out. Is everybody with me so far? Okay. I can figure out the new step size. I don't know why I didn't put that up there, but the new step size is going to be the current period divided by how many steps do we take to get through the full cycle?
5.
So I take 1, 2, well this is a bad example. 1, 2, 3, 4 steps, right? I always take 4 steps.
Yeah.
Okay. So every step I take is now going to be pi. It's bigger than normal because I have more room for my cycle to live. It's twice as long as normal, right? So every step I take is twice as long as normal. Did you guys do this here yet?
No.
So add the pi right over and then What do I do to both sides?
Divide by a half.
No, well, multiply by 2, yeah. So x equals
5 over 4.
5 over 4. Does that match up with this?
Yep.
Totally. Kick ass. Again, very repetitive. The more comfortable you get, you don't have to do all of these steps. But for the beginning, it's kind of nice to see the same thing coming out. So now I say, and again, does everybody understand? I always begin when the input is 0, and I always end when the input is 2 pi. So I'm just seeing with my new function, what x's make that happen. So now I see where I begin for the new function, and if I do this sucks a little bit. Can I kill pi like we did before? No, because this guy didn't have a pi, damn it. One thing I would do, well, what did you guys do? And then I'll tell you what I would do.
I moved the pi over 8 to the right.
Good, alright.
And
2 pi plus pi over 8.
then I multiplied both by 2.
Oh, so multiply both sides by 2?
Yeah.
Okay. So I get x equals 4 pi plus
5 over 4.
pi over 4.
And that's just 5 pi.
No? Did you say 5 pi over 4? LCD,
17 pi
right?
over-
You need an
17
LCD. Yeah, 17 pi over 4. Right, so what would you do, Jeff? I would have done this for the very beginning. You don't have to do this, by the way. If that makes sense, do that. This is what I would do. Whenever I have an equation with fractions in it, I multiply by the number that would kill all of them, right? So then I get 4x minus pi equals 16 pi. 4x equals 17 pi. X equals 17 pi over 4, right? So whenever you have an equation, the beautiful thing is I'm allowed to multiply both sides by whatever the hell I want to except 0. So if I have fractions in an equation, I multiply by whatever's going to kill them all, right? Kill them. Okay. You don't have to do that. I don't care. This will work. Does this match up with what our period's supposed to be?
Yes.
Our period's supposed to be 4 pi, right? Which is 16 pi over 4, and sure enough, this is 16 pi over 4 apart.
16 pi, are you sure it's not 17 pi?
How far apart are these supposed to be? What's our period?
4 pi.
4 pi. So how far apart are these? What's 17 pi over 4 minus pi over 4? How far apart are those?
Oh, okay.
Well, there's 16 pi over 4, which is 4 pi.
Okay.
Good. So you can always check. Your period should be how long it takes you to go from where you start to where you end. Okay, I like it. If you haven't tried to graph it yet, go ahead and try to graph it. This is a little, well, we'll see what you guys think. Normally I give you something without little tick marks on it, so you can kind of like pick your own tick marks, but let's see what you guys do. So this is real quick. I would hope most of you guys would do this. Well, let's see. This is going to be a little bit evil. This is why I don't normally do this, because if I make this pi over 4,
You have to add an extra. Add that.
this would be 2 pi, 3 pi, 4 pi over 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Do you guys kind of follow what I'm saying? Yeah, yeah. So normally I give you ones that don't have these tick marks, so you can pick your own. So maybe on another sheet of paper. You can do it on another sheet of paper. Make your own little graph. Right, this is not the most useful. I was trying to be nice and not being mean. So now if I put pi over 4, every step I take is this big, correct? Let me stop for a minute. My step size is this, correct? So I'm going to take that step, but isn't that the same thing as 4 pi over 4? That's much easier to use because this is over 4. So if I take one step, where do I go?
2.
Huh? If I take one step,
Oh, step, so.
every step is 4 pi over 4,
Yeah.
correct?
Just 5 over 4.
So I'm going to get to 5 pi over 4. Take another step, where do I go? 9 pi over 4. Take another step.
13.5,
Take another step.
17.5.
Is that where I'm supposed to end?
Yeah.
Yes. Okay, so you got a lot of checks and balances. This is what I was saying earlier. This is how much you have to add to where you start and keep on adding it. So if I have a fractional starting place, I need an LCD that makes it easier. Am I doing sine or cosine?
Cosine.
Cosine. My amplitude is 2. So here's where I'm starting, correct? And what is cosine? Where does cosine start?
1. Or about now.
In this case, so it starts at the maximum, correct?
Yeah.
So I'm going to start here. I don't know if you guys are too in the weeds. Are you too much stuck in the details? All the work we did was just to figure out, I know cosine starts up. So if I just knew where I'm supposed to start, I would just put a dot at the highest point. Then if I knew how far away until when it goes to 0, and I know the step size. So all the work we did was just to kind of give myself locations. Pi over 4 is where it starts at the maximum. Then it's going to go to 0 at the next step. I've already identified the next step, 5 pi over 4. So it starts at the max, and then where does it go?
To 0.
0, and then it goes
Minimum.
minimum, then it goes
0.
0, and then it goes
Maximum.
maximum. So sure, all the work we did was kind of a little bit of a slog. It was a bit of work. Sure, it was. But then the beautiful thing is I've done all the work, so the rest of it should be easy, and it is. So now I just got to fill in the shape. I always think that looks like somebody putting their hands up like, I don't know.
It's part of the YMCA.
Yeah, exactly. Somebody dancing some way. Okay. Now again, the only way you're going to get used to this is to do problem. If only I signed, oh yeah, I did. So if you do the homework, you'll get practice with this. As you're doing the homework, you should have this completed problem sitting next to you so you can sort of reference it, right? Okay. So, let's talk about what trig functions have we not graphed yet?
Tangent.
Good, tangent. Is that the only one?
And then secant.
Secant, cosecant.
Secant, cosecant. So here's the funny thing. Everybody look at this side. Right, this is this side of the pig. Okay. What? Oh, Jesus. All right. What if the problem had instead been 5 cosecant? Okay. So this is what I want you to, this is the beautiful thing about this. When I memorized values for trig functions, I didn't have to memorize cosecant because I just remembered that cosecant is 1 over sine, kick out. So whatever sine was, I just had to reciprocate it. Less shit to memorize is always good. Similar things happen for the graph. Cosecant is 1 over sine, right? So help me out. For example, right here, this is not a great example. I shouldn't do this one. Let's just do a sine. That's a good idea, Jeff. I did a sine function earlier, didn't I? There it is. So everybody still got this sucker that I made you graph? Okay, let's take a nice unshifted one just to start with. If I want to plot, yeah, I'll do it this way. If I want to plot cosecant x, it's 1 over the sine, correct? So can somebody tell me what's the value of the sine right here? 1. So what's the value of cosecant here? 1 divided by 1? 1. Okay, everybody kind of with me. Cosecant is just 1 over sine. So on one level, it should make sense. If I can graph a sine, I should be able to use that graph to make cosecant. Because cosecant's 1 over sine. So help me out. Just to give it a specific example, at pi over 4, actually let's do something a little bit easier. At pi over 6, what is sine?
1/2.
It's very cool that sine of pi over 6, sine of 30 degrees is 1/2. So what's cosecant?
2.
2. Oh, shit. 2. Right. I should go back to my paper. Yeah. So, if I'm trying to graph, the reason I want to do that is to have different colors, but I can try to do that. Yeah, here we go. Get back here. I can use blood red. Okay. So if I want to graph cosecant, 1 divided by 1 is 1. By the way, you're not always going to have to do everything I'm about to do. There's a shortcut, and we'll get there. At pi over 6, the sine is 1/2, correct? So the cosecant would be 2. At, you could do it, Jeff, at 5 pi over 6. What's sine? 5 pi over 6, what's the reference angle?
60.
Pi over 6 is related to 30. So it should again be 1/2. And you can see on the graph, it kind of makes sense. Do you see how the graph relates to sine of pi over 6 is 1/2, but also sine of 5 pi over 6 is 1/2, right? So what's the cosecant here? 2 again. As this gets closer to 0, what happens to 1 divided by that? Gets stupid big. Does everybody agree that somewhere sine is 0.1? Do you all agree that somewhere there's an output of 0.1, yes? And what's 1 divided by 0.1? What's 1 divided by 1/10?
10.
Freaking 10! Now, does anyone understand what's going to happen here? Help me out. Help me out. I really want you guys to somewhere there's a place where sine is 0.1, yes? So cosecant would be 1 divided by 0.1. That's 10. You with me? Do you agree that somewhere there's sine is 0.01? That's really close. Somewhere sine is 0.01. What's 1 divided by 0.01? 1 divided by 100th. Frickin' 100, yes? Has anyone ever heard of something called an asymptote?
Yes.
So this is going to be one of my favorite words, asymptotic. Sounds like a kind of drink.
Tonic.
Yes, I'll take an asymptotic. Thank you very much. So what this is doing, what that drink would do is take you to infinity. So this will take this to infinity. This is going to go like crazy. It looks kind of like a parabola. Do you guys agree?
Mm-hmm.
Do you see how this leads to a freaking shortcut for cosecant graphs? If I graph the corresponding sine function, graph that. And then just, what do you think is going to happen over here? Aren't all my outputs negative? So cosecant, whatever this is, it's going to be 1 over that. So it's just going to be a parabola going down now. It's not really a parabola, by the way. But it's going to look like a parabola kind of opening down. So it's going to be a cup up and a cup down, and it's just going to continue forever.
Well, that is a type of parabola, if I remember correctly.
Say again?
There is a type of parabola that goes,
No, of course, y equals negative x squared would go down.
Yeah.
That's not parabolic because the curvature is not parabolic, but we don't have to know all that shit. It looks like a parabola, so that's good enough, right? And just to remind you guys, oh, Jiminy Jeebus, there it is. That's amazing how quickly. I gave you this a while back. We're just kind of now figuring this shit out, right? Do you see how a sine would fit
So
in there?
now
Do you
we're
see that?
4.3. We're slow.
Yes. I think I don't know. I just know shit. I don't know where I am in the book.
What
Sorry.
do you mean? You have the book there.
I do. It's way over there. I don't want to see it. So, it's not surprising then that a secant function is going to have the same shape, except it's going to be shifted over a bit, right? Do you guys all agree? That's why this thing, so why does this look like this here? Because sine is maximum this when they both agree. It's 1 over 1. But now cosine is at 0. It's 1. So that's where it's going to kind of have its up part. I don't know if you guys are with me in that. So here's cosine coming in. Wee, wee. Oh, this is horrible, that fall. And then the cups just sit on the top and bottom of that. I don't know if you guys are really with me. It's just because it's 1 divided by. So anywhere that the cosine is 0, I'm going to have those asymptotes. Where is cosine 0?
9.
Pi over 2. So at pi over 2, do you see how there's an asymptote at pi over 2? There's an asymptote at 3 pi over 2. There's an asymptote at everywhere that would get me back to the y-axis, because cosine hates it there. So secant, here it is, secant would be undefined at those places. 1 divided by 0, that's undefined. That's why there's got an asymptote there. Are you guys understanding? So if you get to a point where you're really comfortable doing sine and cosine functions, cosecant and secant is just an extra step. You graph a cosine or a sine, and then you just put the cups on top and bottom, right? So again, if this problem we just did had been this, and we didn't do this, the one I did, then I would have just put cups here, cup there, there would have been an asymptote here, there would be an asymptote there, and an asymptote there. You guys, it would just be one step at the end, just put these on there. Does that make sense? And normally if I'm going to do a cosecant, I would do this one dotted, because it's not the answer yet. So if I give you a cosecant question, you answer it as if it was sine. You graph like a dotted function, and then you put the cups on the top and bottom of it, right? Kabam, yes.
So would the asymptote always be where it meets in the midline?
The asymptote's going to be anywhere where the original function would be 0. Because 1 over that's going to be an asymptote. But say it again.
Like where it meets in the midline?
Where it meets the midline. Oh, I see. Yeah, because that's where it's. Oh, I see. So if it's been shifted, yeah. Okay. So that's the general way you can remember. Wherever the original function would hit the midline, that's where there's going to be an asymptote, because that's where there would have been 0. Yeah. Okay. All right. So sine and cosine leads directly to cosecant and secant, which kind of makes sense. So the only thing we have left that's going to look very different is tangent. And then, of course, cotangent. What time is it? All right. I always run out of time. So let's talk about tangent.
10:37.
Say again?
10:37.
Thank you. Let's talk about tangent and cotangent. All right. So when we first investigate the graph of a function, we can make a little table of values. Let's do that again. Let's do this. See if you guys are cool with this. I'm going to start at negative pi over 2. Yeah, this will be good enough, I think. There it is, Jeff. Pi over 4, pi over 2. Okay. This should be enough to get the general idea.
Yeah, well, I want to get rid of that stuff on the board right there.
Oh, I'm sorry. Thank you. I just look that way sometimes. Hi. Hi. Okay. All right. Let's start here. What's the tangent of 0? 0. Because tangent is what over what?
Sine over
Sine over cosine. What's sine of 0?
0.
And what's cosine of 0?
1.
0 over 1? 0. Cool. Pi over 4 should be a nice one. Like what's tangent of just positive pi over 4?
1.
Because that's where sine and cosine are equal, correct?
Mm.
What do I have to be careful about back here? What quadrant am I in? If I go, from your perspective, if I go negative pi over 4,
Quadrant 4.
I'm in quadrant 4. What's tangent sine going to be? SIGN?
Negative.
Negative, because the sine and cosine are different signs, correct? And I'm taking the quotient of sine and cosine. If they're different signs, I'll get negative, so it's negative 1. Okay, I love it. Some of you guys look like you want to hurt me. That's okay. I'm sorry. This is old shit, by the way. Yes? Some of the new shit's about to happen. As I approach pi over 2, remind me, tangent is sine over cosine, yes? What is cosine getting closer to as I approach pi over 2. 0. So just like what happened with cosecant and secant, I am getting something that's dividing something closer and closer to 0. So what's going to happen right here is an asymptote. It's going to go to infinity. So it's also going to happen over here. For the same reason, the cosine's on the bottom. So wherever cosine is 0, I'm going to have an asymptote. It's going to go to infinity. Okay, let's stop for a minute. So let's try to graph this weird thing. So I'm going to put negative pi over 2, pi over 4, 0, pi over 4, negative pi over 4, pi over 4, and then pi over 2. At negative pi over 2 and pi over 2, I'm going to put an asymptote because that's where cosine freaks me out, right? I'm dividing by 0 there. Freaking. Tangent of 0 is 0. That's a good place to start. Tangent of pi over 4 is 1. Tangent of negative pi over 4 is negative 1. And then I have to kind of approach that. So does this graph look sort of familiar to anybody?
Oh.
It kind of looks like a cubic, right? X cubed. I don't know if you guys are, so like x to an even power looks like a parabola, x to the odd power
Yeah.
looks like a cactus. Okay. It's a little bit like stretched out. It gets a little weird to graph in the middle. It's not supposed to be straight, but it's kind of weird to graph, right? Every single trig function repeats forever. Do you agree? Because they keep going around the stupid unit circle going insane. So it's going to be over here too. It's going to be over here too. Yes?
Well, isn't it just like just the unit circle, like just unraveled?
Totally. I love it. So yeah, I've got some nifty animations I can show you guys later. Holy crap. So what is the period? I don't know why I was using my red pen. You can't see that as well. I'm sorry. What is the period of this? Can you guys see how long does it take to create one shape that it repeats? How long does it take to create that one shape that repeats? How long?
Pi?
Yeah. This is pi apart, correct? Pi over 2 minus negative pi over 2, pi over 2 plus pi over 2 is pi. The period of tangent is pi. Period of sine, cosine, secant, cosecant, they're all 2 pi. Period of tangent, it gets done in pi. Okay.
And then just likes to stand out, huh?
Yeah, it's got to be different.
It's always not under.
And it makes sense because tangent's the only one that's really the division of 2 trig functions, so I would expect it to be kind of weird compared to the other guys.
And cotangent would be even weirder, right?
Cotangent, just to cut to the chase. Well, here, I already gave you this so I can show you. So here's tangent. This is what I just did. So here's what I did, right? We normally consider this to be the one we graph. We always graph around 0. So negative pi over 2 to pi over 2. Now real quick, what's on the bottom of cotangent? Sine. So where is its asymptote's going to be is where sine is 0. Where is sine 0?
At
0,
0, pi,
pi, right? So that's why here, for the cotangent, there's an asymptote at the y-axis, there's an asymptote at pi. You see that? The other weird thing is it goes the opposite direction here. Right? So we could make a table of values, we could do all that stuff, but it's got the same basic shape, which makes sense because tangent and cotangent are directly related. Okay, maybe. Where's tangent 0? Isn't it 0 right there? Isn't cotangent 1 over tangent? So if tangent 0, shouldn't there be an asymptote for cotangent? Okay, same idea for the cosecant, secant, same idea. So tangent, let me give you this, we'll do this next time, but let me give you this.
So, for cotangent,
I should probably hold on to this, but I'm going to give it to you.
so for cotangent, an asymptote would actually be on the y-axis, right?
Coach, yeah, exactly. And can you see that up there? You all have this sheet. You should have this sheet, right? Okay. And you're like, don't tell them anything. Keep them in the dark.
Wait, I'm confused now. Where does it say 5.1 and 5.4?
Thank you. Yeah, we don't have enough time to do this today.
One of my friends gave it to me.
Somebody behind you, Chad. Thank you. But just real quick, if I were gonna graph this one, I would graph this using, what would I graph first? I would graph
You'd use, sine.
sine. I would graph sine first, because then cosecant are just the cups that live above and below the sine.
Yeah.
So if I ask you cosecant or secant, you just graph the corresponding sine or cosine, and then you put the cups on it, and you're golden, right?
Would it still stay the same if you just changed it to sine? Like you wouldn't have to.
Yeah, you can pretend like this is sine, graph that with a dotted line, because it's not the answer, and then put the cups in the appropriate place. You also have to put the asymptotes, right? So obviously we'll do this in an example next time. And then the tangent, I call it like an amplitude, but where did I put my tangent? Do you see how at pi over 4 it hits the amplitude number? I need you to understand, if I would have put a 2 here, wouldn't this have been at 2 instead?
Yeah.
So do you understand there's no amplitude here? Why is there no amplitude for tangent? Because it freaking goes to infinity, negative infinity. No, but I could still use the number in front to know where pi over 4 goes. So obviously we'll do at least this example next time. But that's enough for today. We're basically out of time. So have a good break. We all deserve it and need it. Come back mentally rested. So don't come to college next week. Nobody's going to be here.
No, you'll be crazy here.
You can come, but I mean, ain't nothing going to be open.
No one will be.
Yeah, Mr. Waller, if we still have questions on article 1, I can still email you.
Yeah.